Um, Thanks, guys, for coming. Sorry we're a little bit running late, but this is our...
This is actually our first meetup in person since COVID happened, so it's really exciting. And we're at a new location, Saxworks, and so far it's a beautiful location. Right.
Yeah, so I work here at HPC, and these are kind of like co-working spaces, we're partnered with WeWork. And yeah, we're excited to get back to in-person events. So we have Hudson Space Systems tonight, and we have Sat Search on the 27th, and we have a lot more coming up. So without further ado, we have Hudson Space Systems, and the talk today is called Science in Space, and it's Microgravity as a Service. Is that right?
Yeah.
Yeah.
Cool.
Thanks, Mike.
Thanks, guys.
Thank you.
Hi, guys. It's nice to have the opportunity to chat with you all. We're all collectively Hudson Space Systems.
So to introduce the four of us, I'm Monica. I'm our COO, and I'm our head propulsion engineer. I have experience interning at NASA, at Marshall Space Flight Center in their thruster design. I also currently work as well for Army Futures Command at DevCom AC, and I work with novel rocket technology. So right now I'm focusing a lot on rotating detonation engines, which is really cool.
And my name is Dakota. I'm our CFO. I manage our finance team of one. That's me. And in 2019, after graduating with my bachelor's in chemical engineering and my master's in materials engineering, I came to work full-time for Hudson Space Systems.
My name's Nathan. I'm our CEO. I do our systems engineering and integration and anything else that people don't want to do that particular day. I'm finishing up my master's in space systems engineering and working for the company full-time. And hiding over to our right, we have Ben, who's our CIO.
Everyone, I'm Ben. I do all the avionics, all of the software and hardware development for our launch vehicle and ground systems.
And then we're joined digitally, but not in person, by Will, who's our CTO. He has experience in fluidics design, and he currently also works at Valcor. Cole, who's our first employee and does our avionics development alongside Ben, and our two awesome advisors, Coram and Igor. So we want to talk to you guys tonight a little bit about microgravity, science in microgravity. What is it? Why do people get up to it? Explain some cool applications, walk you through a little bit of what we do and how that applies to microgravity science, and then talk about manufacturing in space and the future of manufacturing. So without any more hesitation, let's get into it.
Sure. So I'm going to walk us through first quickly who's sort of doing science in space right now. Since the 1980s, the commercial space market has been booming, and starting with some applied sciences like agriculture and pharmaceuticals, and then feeding other harder sciences like biology and physics, almost every field has at least one research player in the spaces market right now. These experiments are typically pretty small. They hitch rides on board ISS resupply missions, or they spin freely through space on personalized satellites. And so for the time being, research in the microgravity environment is fairly limited to those rich enough to cut a large check or lucky enough to win a government grant. So before we talk about widening that field, as we hope to do with microgravity as a service, we're going to talk a little bit about why there is an interest in space to begin with. So the space environment is unique for a few major aspects. For starters, it isn't really an environment. It's actually the easiest place to find something completely devoid of what we on Earth consider an environment. So for those interested in studying extremes, like the lack of any atmosphere, or for those interested in creating pure inorganic surroundings, space is essentially a playground. The second reason, and arguably more important, is the microgravity aspect, the perceived lack of gravity, or what science fiction calls weightlessness. So let's not get ahead of ourselves. Before we talk about the rest of the science in space, we're going to talk about what microgravity is, and why things that are in space don't really not feel gravity. You would need to travel a really long distance, way far away from the Earth into the universe, to find a place where there is actually negligible gravity. All of the mass that's found in the planets, stars, and galaxies means that anything, anywhere in our universe always feels at least the slightest bit of gravitational pull. So since astronauts on the ISS are so close to Earth, they actually feel approximately 90% of the gravity that we do here on the surface. So the big question is, why do they appear to float? Why do we call this microgravity? And we're going to throw it to the video really quick to find out.
The answer is that the space station is falling towards the Earth. But don't worry, it was designed to do that. Earth's gravity, in combination with the tangential momentum of the ISS, makes sure that the space station stays in an orbit around the planet. And everything inside the space station is also falling at that same constant speed. That's why objects aboard the ISS appear to float. They're all free-falling toward the Earth at the same speed as the ISS.
So, now that that's out of the way, let's start with the big picture. By removing gravity from the equation, scientists are better able to understand the underlying principles that are key to our natural world and the things that they're interested in finding out more about. Dominant gravity-assisted mechanisms present in transport phenomena, cellular reproduction, chemical reactivity, and more are all muted, allowing us to identify, enhance, and closely study some of the weaker mechanisms that are at play in those systems. So that means that in liquids, cohesion and surface tension become predominant, which is why they tend to become spheres, rather than adhesion, which is what sort of glues it to the wall of a flask or a beaker. Sedimentation is replaced by near-perfect Brownian diffusion, and convective transfer is rendered almost useless, leaving only conduction and radiation. That and cellular cultures cure, reproduce, and mutate many times faster. So this is across many industries, across many fields, and every scientific discipline has a different take on how to take advantage of some of these features and quirks. Most of them overlap, so you see we've sort of accumulated biology, pharma, and medical around the cell, and materials, physics, and fluids around more of the buckyball-looking shape. Biologists get excited because stem cells exhibit enhanced stemness, and cell-based disease modeling can be accelerated. Microorganisms and secondary metabolites react and evolve differently in space than on land, and in medical research, where the key to designing things is to make them smaller and less obtrusive in the human body, space is able to create new alloy development and precision microfluidic systems for inside those devices. So the unique properties of fluids and microgravity also focus on obvious fields like fluid dynamics, interfaces, separations, but also things like electrodeposition, stability, and emulsification, which move more into the manufacturing side that Nathan's going to talk about later. Additional benefits can also be found in nonlinear optics and the study of flame science and many, many other things from biology, physics, and chemistry alike. So let's talk about some specific examples. This is our first one. ZBLAN optical fibers, also called ZBLAN. They're named for their constituent heavy metal fluoride complexes. They are a family of glasses that are capable of revolutionizing the optical transmission world. So their transmission window is 3 times greater than traditional silica glass, which routes to people's homes in Google Fiber, reaching from 0.3 microns ultraviolet to 7 microns infrared on the wavelength spectrum. Their theoretical maximum attenuation loss is 100 times smaller, meaning that we can go 100 times further without having to introduce repeaters into the system and potentially disrupt the communication. This combination provides a greater application than silica glass for medical, remote sensing, lasers, thermal imaging, and spectroscopy, and much, much more. Unfortunately, these ZBLAN rare earth metals tend to form undue nucleations when they are processed on Earth, and they precipitate into unwanted phase separations, which cause optical unclarity and can cause communications to get scrambled.
They clump up.
They clump up, yeah. So several tests, which were spearheaded by the Physical Optics Corporation and NASA, and then have been continued by Made in Space and Thor Labs, to name a few, have proven that creating ZBLAN in orbit sort of gets rid of a lot of these problems. They produce fibers with increased optical clarity, and payload size doesn't really constrain how long you can make these fibers. So 8 kilometers of fiber can be made by sending up 1 pound of preformed glass in a cube, essentially the size like a foot by a foot by a foot. So by sort of working all of these factors in, and in a competitive market, we could raise the fiber market to within about between $175 and $1,000 per kilometer of this fiber, providing a pretty healthy return on investment. And secondly, let's talk about some 3D tissue cultures. So in the case of Vivo Biosciences, which the work was then continued by Merck and others. They were testing biological response systems, and cultures have become increasingly helpful in the pharmaceutical and medical research industries because drug trials can be done on test tube tumors. And the burgeoning organ-on-a-chip market is banking on successful development in this field, growing live tissue outside of a host. But this can be pretty difficult because cells need complex nutrient signaling and waste pathways so that they don't die. And so they are normally built on submerged scaffold systems. They are built around an armature that is sunken into a liquid that provides them with the food that they need. Under gravity conditions, these culturing cells tend to form two-dimensionally, though, which isn't great. They don't appear like natural three-dimensional organs inside a body. And also, they sometimes slough off of the scaffold and collect in the bottom of the solution. In space, though, there is no bottom of a petri dish. So the cells are more likely to clump together and form in their natural shapes, providing a more realistic environment for in vitro experiments to be done on them.
So given all these super interesting things that we can do in microgravity, how are people currently actually testing in microgravity? Well, the quickest and easiest and cheapest way to do it right now is actually on the surface of the Earth. Usually people use drop towers first, which are pretty much exactly what they sound like, which is everyone's favorite carnival ride. You drop something from the top of something really tall or into a hole that's really deep. So NASA, for instance, has two at Glenn, which are probably some of the most used ones. They have a tower, which provides 2.2 seconds of time, and a shaft that provides 5 seconds of time. And they use those to test things like fluidics and combustion science, and even to start testing new things they're going to send into space for the ISS, so new equipment that they want to test out first in microgravity. It's, again, pretty cheap. And as you could see, these all happen less than 10 seconds. So you can start learning a lot even from that short period of time. The next thing that people do is tried and true. They send up a suborbital rocket. Which is exactly where we're going to start out too. So that's a parabolic flight. It goes up and it comes right back down. These are really popular, and they usually offer between 3 and 20 minutes of microgravity. So our favorite Blue Origin New Shepard and Virgin Galactic VSS Unity, which everyone has heard about pretty recently, both fall into this category. They're doing it for humans, but they also offer space on both of their launches for microgravity research. People like Exos, UP, and Rexus all have different rockets doing this as well. So the next step up is kind of entering the big leagues. You have 2 more options at this moment if you want still more microgravity time. So the first is deploying your own CubeSat. The unfortunate part about this is you can't get that research back, and you have to book a spot on a heavy launch vehicle. And additionally, you're acquiring the additional cost of payload design and integration. There are companies that have popped up that have to help you in this space, people like NanoRacks and Space Pharma and Space Tango. They don't necessarily provide the launches, but they're helping you with the payloads. They're helping you figure out where you're going to put that payload. But of course, that's a lot more cost. Designing for the harsh environment of space is pretty tricky. And then you have to figure out how are you getting data back from them, and are you learning what you need to learn? You can't really fix it once you send it up there. And then if something goes wrong, you're just going to deorbit it and lose all that money. And then what the bigger companies are doing in the big leagues is eventually just sending up their experiments onto the ISS. That's what Merck and a lot of pharmaceutical companies are doing right now, because you do have a ton of experimental time there, and you are going to be able to retrieve it once you get it back. But you're paying a ton of money for that, and you're swimming through endless stacks of paperwork. We've talked to researchers who've launched for the ISS, and they say that it just doesn't end. Like, the paperwork is like absolutely death-inducing. So we'd really want to avoid that, right? There's a lot of helpful benefits to testing there. Many companies have seen like 1.5-year decreases in go-to-market time, and huge possibilities, as we've talked about. But we want to make that available for people without all those challenges. So as we've talked about, this is kind of where the problem lies. The average time to launch is 1.5 years. Microgravity flights are usually $15,000 per kilogram on average, and customers usually need to engage with multiple providers to reach their end goal. Sometimes they're not just booking their flights, but they're having someone design their payload for them, because obviously if they're a PhD in biosciences, they might not be able to make a super advanced payload to go into space that can withstand radiation. And resources like the ISS are over-constrained. They can't really let us explore manufacturing in the way that we want to, right? A great way of looking back at that is for the case studies that Dakota had mentioned. Both of those startups weren't able to continue their research even though they were super promising because the financial burden of testing in space. So Made in Space and Merck were actually able to pick up their research because they had the money to do so. So this is where we come in. This is what we're hoping to solve, and just talk a little bit about what our vision is for how we can improve this market. We want to offer what we call microgravity as a service, which is a vertically integrated service. It's your one-stop shop for microgravity, which should eliminate costs and barriers. So first, you schedule, which is as easy as looking at an online calendar, plus a really well-designed UX. You should be able to book your launch, configure your payload modules, communicate with our team, view your flight profile, download your data, and more from your portal. So we want to make this really easy for researchers, regardless of what you're doing. Stop jumping through hoops and dealing with tons of online contact forms for a custom payload. Next, we integrate your payload. We want a low friction experience that eliminates some of those implementation providers, and your payloads are well hosted. Our modules will be pre-built for experimental and manufacturing needs, and they'll be configurable with in-flight triggers, data acquisition, power, telemetry, temperature control, atmosphere control, pressure control, all that. Because we realize that everyone's going to have different research, so obviously you need to configure that. But we hope to make that easier to personalize it, but to be able to do so within this prefab that kind of makes it faster and easier for you to do that too. And then we launch. Our launch system is going to be reusable. It's ultra simple, it's pressure fed, and a fast turnaround time for our propulsion system with taking advantage of 3D printed engines and COTS systems. This allows for rapid relaunch and iterative experimentation. So that leaves you to do you. Whatever you're doing in space, you'll get your results quicker without worrying about the how-to. And finally, good research can't really be done once, right? Reliable manufacturing doesn't happen on the first try. We're hoping to make it possible and affordable for you to be able to actually hone down these processes and research to something that helps you back on the surface of the Earth or makes you money here. So with these services, we hope to be able to democratize space for these sciences. There are more applications in the hard sciences in LEO, actually. However, the money, the markets in life sciences. So unfortunately, the paying life science experiments usually take longer to perform. So we hope that as we shift from LEO to orbital science experimentation, that'll allow us to shift our capacity to more life science focused experimentation as well. So really quickly, just to show you how we hope to make that happen, this is our product roadmap. We hope to allow microgravity as a service to reach its massive market potential through this nice step-up system. So we're going to start with our suborbital reusable launch vehicle, which is kind of our proof of concept that offers 3 minutes of microgravity. And that might seem short, but again, drop towers start at like 2 seconds, and people do those experiments regularly. That's a helpful amount of time. So that's a great place to start, and that'll offer pretty rapid launches. Our next step up from that will be our high altitude reusable vehicle. That'll offer 10 minutes of microgravity. That'll also allow us to build towards a recoverable orbital factory, which will be super LEO. That'll allow for essentially infinite amount of time to do your manufacturing or research, and just like you would on the ISS, to be able to get your research back. But again, without that paperwork. And then just to show you on a closer look, that standard model is our first model. It's our tech demonstrator. That'll be an 8 kilogram payload. Then we'll jump up to our next model called supersymmetry, and that'll be 10 times that payload capacity. And then finally, that's our orbiter, and that's 8 times that last one. Yeah, stay as long as you like there. And that's just a quick visual of what those payloads will actually look like. On the left there is our standard single payload offering, and then that's how it'll be tessellated across the vehicles we'll be offering.
So we've talked a lot about the cool science being done in space, the people who are doing it, and maybe how we want to help them do it a little bit better. But research is just the starting point. We really want to facilitate the future of manufacturing in space. So the first question is, why would anyone want to do this? Would you mind skipping? Sure, thank you. It's hard enough just to launch something to space, much less build an experiment, much less manufacture in the microgravity environment. But it turns out the benefits are pretty compelling, and they're very similar to the reasons that we want to research in space. You don't need scaffolding, both actual scaffolding if you're building something physical, or biological scaffolding if you're working with cells, building organs, any sort of growth. The extreme environment is just as valuable for manufacturing as it is for research, for vapor deposition, for manufacturing ultra-pure crystals and glasses. If you want to build something big, why would you pay to launch that material into space when it's already there? You can harvest that material in orbit, around the Earth, around the Moon, from asteroids, and use that to build your project. And finally, if we want to explore the solar system, we've got to figure it out, and we can't figure it out on Earth. We've got to figure it out in space. And we need to be able to build that stuff in space. So just like research, there are existing products that can be manufactured better in space. There are novel products that can be manufactured for the first time only in space. And there are applications for human spaceflight. There's a clear path from many of the areas that we talked about in research to manufacturing. So I'm sure a lot of you have heard about monoclonal antibodies recently in the news. They're a type of protein crystal. They target specific antigens, and protein crystallization is a mechanism that is enhanced and accelerated by the microgravity environment. So there's a vast potential for novel pharmaceuticals to be manufactured in space, especially high-value pharmaceuticals for urgent conditions that we struggle to address on Earth, like cancer research. Deposition phenomena in the vacuum environment without contaminant allows us to produce advanced semiconductors. There's already ongoing research, but in a large scale, we could perhaps produce future processing advancements in space, fly them back to Earth. The list goes on, and we'll jump into a couple examples in a bit. One really exciting case study is Lambda Vision. It's a US-based company who's doing research on the ISS right now, growing very specific proteins that I'm not going to try to pronounce to develop artificial retinas. These prostheses are so delicate. The weight of gravity and the atmosphere on the Earth crushes the layers. It prevents proper growth. So the only way that they can develop these is in microgravity. For them to be properly functional, everything has to be super precisely oriented. And so they found that in doing this microgravity research, they're able to produce high-quality retinas. And this is a perfect opportunity for someone to manufacture a novel product in space and then ship it back to Earth. So this sort of stages us well to think about future applications. What can we do with this technology? What research can be extrapolated into awesome sci-fi products that maybe we're imagining now, but 10 years in the future could become commonplace, just like I'm sure 10 years ago no one would expect that there would be rapid space launches with recoverable rockets that land themselves. If you tried to explain that to someone, they would say that that's never going to happen. I think the same thing is going to happen with in-space manufacturing. So things that we talk about when we talk about space manufacturing are vital materials for human growth and vital materials for space growth. People have been talking about graphene forever on Earth. but the advancement has been super slow. The advancement in space has not been super slow. People have been able to produce graphene in larger sizes in space, I believe 10 times the size that they're able to produce in labs on Earth. So imagine if you could take graphene, produce it in large quantities as raw material for future spacecraft development. On the flip side, we're just sort of getting into organ on a chip and bioprinting organs in space. But in 5-10 years when that technology matures, we might be able to produce organs in space on demand for conditions on Earth, so we could potentially eliminate organ transplant lists. So to pull everything together that we've talked about, we can build and assemble in the weightless environment huge structures that are impossible to build on Earth with materials that are impossible to make on Earth, like flawless optics, like large graphene structures, high quality vapor deposited surfaces. So the possibilities are really endless, and they start with having a good way to manufacture in space. As Monica and Dakota were saying, the opportunities are there, but the existing resources are over-constrained. So if the resources were there, imagine what we could do. Like, this is the future, and we want to make it happen. So if you guys have questions, both in person or in the Zoom, please let us know. We'd love to engage.
Clearly, we love talking about space. So.
I have a bunch.
See if we can.
Yeah, I have a quick question. I know I'm walking a few minutes late, so forgive me if I'm repeating. So you showed a slide where you had kind of a progression from like drop the balloon, rocket, and then transporter. I can't remember the exact terminology you used. Where are you currently in that life cycle?
So we're starting out with a suborbital rocket, so we'll be that's first step up, and that's to build our technology. I think there's quite a history in space companies that build themselves and jump right into big rockets and fail, right? Because you don't have that history of information there, you don't have that competency under you. We think that's deadly. So we don't want to jump there. So we're starting out with a suborbital rocket in order to afford small-scale, rapid testing for researchers who can use 3 minutes. We have a couple letters of intent for that already as well. And then we're jumping into high-altitude suborbital and then into a recoverable orbital factory, which will be those payloads, but in super LEO. So you can get there quickly, and you can stay for like good intervals of time for up to an hour, really.
Yeah, exactly. Very low Earth orbit is currently underutilized because most of the satellites being launched need to be sent to a particular orbital inclination and altitude, and very close to the Earth is not great for most applications, but it's perfect if all you're interested in is the microgravity environment.
And are you purchasing rides on suborbital rockets, or is that part of what you're
That's part of the
designing
stack.
and building?
We're building that entire stack from the website to the hosted payloads to the launch vehicles to the logistics.
So we've got a prototype vehicle sitting in our lab already
Okay.
that we're working on.
And as a startup, we're trying to be as sustainable and smart with our money and time and resources as possible. So this progression through these vehicles is not only helpful to, the time and the place that a lot of researchers need their things sent up, but also will help us in sort of parallel manufacturing and technology understanding for ourselves, because by learning about the suborbital reusable launch vehicle while we're building the high altitude vehicle, we can sort of apply some of those changes that we're like, oh yeah, we should have thought of that, to that next vehicle as we're building it for bigger and better payloads.
Cool. Very good.
Thank you.
So you guys mentioned reusability, but you didn't say how you might achieve it. So that's a secret, or do you guys have a plan?
No, we just didn't want to dive too much into the technical details because we wanted to focus on the other technical details.
Focus on the service we're offering, not the product that makes it happen. But
Yeah.
we love to talk about it.
Yeah, we love talking about the launch vehicles, and I will explain, but it's hard to fight against the consumption that we're just a launch services company, because that is only just a core of our stack. We do offer the entire microgravity research service. But the launch vehicles are recoverable and reusable in their design. They're built out of unibody composite structure with integral tanks. And then we just use a simple multi-stage parachute system to recover them. Nothing fancy, and that's the whole point. We keep it low cost. The rockets are designed to sort of fail backwards, so the least expensive components fail first on impact, not in flight, so that we can inexpensively and rapidly refurbish them.
Yeah, about 95% of the individual components on board a rocket per launch are designed to be reused in the next launch. So we hope to then recover them, find whatever has broken during that flight, refurbish that piece only, and then launch, hopefully, mostly that same rocket again.
Yeah.
Ship of Theseus philosophical questions aside.
Yeah, the whole purpose of building our own launch vehicles as opposed to buying space on another is so that we can control the cost and control the timeline for customers. It's not going to be cost sustainable in the small term. It's going to cost us way more, but in the long term, it will be incredibly cost sustainable. The unit economics are excellent, and right now it's the only way that they work out.
There was a question.
I guess 2 parts. Like, what, how many years do you think it'll take to go from suborbital to in orbit? And then secondly, if you're gonna is there a reason you can't take the same testing payload and negotiate with NanoRacks right now to provide your medical researcher customers and just kind of charge out the launch cost and whatever fees? So at least you don't lose that business until.
It's a good question.
Yeah, it's more important for us to build a service that's accessible, and that sort of cost plus structure is one of the big reasons that people can't get into research and manufacturing presently, because you have to pay for an implementation provider and pay development costs and pay for launch fees, and then if you're launching to the ISS, pay for additional storage and usage fees on the station. It's going to take us more time, and it's going to take us longer to acquire customers, but we're going to build a better service. Right now, the space market is rapidly expanding, and there's not a ton of infrastructure. So building an infrastructure like microgravity as a service is going to be essential. The market is huge, and it's only getting bigger. So there's no harm in waiting a little bit to do it properly, in our opinion.
Did you feel like that answered your question? Okay.
The first question was how long would it take to
Oh!
go from suborbital to orbital?
2 to 4 years, depending on money and what explodes.
We get asked online, how does your cost compare to existing?
It's complicated. Do you want to?
Yeah, so in the launching sphere, like Nathan was saying, the cost plus structure sort of stretches some of these fees. What we're targeting right now is a flat rate charged at cost per kilogram. So if your payload is 1 kilogram, we charge you for 1 kilogram. If your payload is half a kilogram, we charge you for half a kilogram. And the way that the market is currently structured, you can sort of think of it as heavy launch, medium launch, and small launch. So heavy launch example would be like Falcon Heavy with SpaceX. And then the medium launch and small launches we don't really hear about as much on the news all that much because they're not as, wow, big, impressive, amazing rocket going up into space. But so our cost structure is low compared to our competition.
Yeah.
I think 40% lower was the last I had saw. I was looking at this source earlier today that shows the market average for small launch, which is what we're classified in, is about 15,000 right now.
Yeah.
You can find some cheaper, some more expensive, depending on your country. Yeah, per kilogram.
Yes.
Thank you.
So the comparison that we use right now is that the average is 15K per kilogram to launch something suborbital or light launch. And we're charging for our first generation vehicle 9.5K and for a second generation vehicle 12K. And whilst those costs are getting close, when you pay for a payload on a launch vehicle, you're just paying for a space on a launch vehicle. But when you pay our cost, which is substantially lower, you're paying for that whole stack. You're paying for the payload, the integration, the launch vehicle, the recovery, the logistics, all of the bits and pieces that we provide to make it a seamless experience. And the reason that it's that much cheaper is because we vertically integrate, because we bring everything in-house and optimize it.
Yeah. And one more note on, sorry, the finance thing is clicking in my head now. The note on the average is that's a global average. So some people, depending on where in the world they are restricted for whatever reasons from launching with certain providers. So that could raise or lower their cost of entry respectively.
And I'm sure as soon as we say it, the average costs are going to be incorrect because the costs are constantly changing and people are also pretty proprietary with their details. So don't be surprised if you go and Google this and the cost is way higher or way lower on average. Those were the numbers from 2019, I think. Mm-hmm. It's the most recent comprehensively compiled data.
Hi. So why is it based in Hoboken? And you launched from there? So did this come from one of the programs at Stevens for the rocket launches? I used to attend Stevens.
Oh, cool. Yeah, cool. We all attended Stevens, and we're living in Hoboken, and that's why we're based in Hoboken.
I know where that spot is. That's that, like, by the cliff.
Yeah,
precisely. It's a little building that looks like it's sort of falling down in the back industrial corner of Hoboken.
And that's us.
Yeah.
Yeah, it was sort of easy for that to be our spot for now while we're in just the development phase. Once we start our launches, they are not going to be right across the river here because that's too many airspaces you have to deal with, and no one wants that happening in Hoboken. So we're looking at launching from the western United States where there's a little bit more land for cheaper, but again, that is, like we're talking about timelines a little bit further down the road.
Yeah, so there's some compelling options like Spaceport America, places that are developed tailor-made for this type of vertical launch.
And with regards to our origin, we started not necessarily out of a program at Stevens. We started this as our senior design project, and then we raised $500,000 to actually develop our prototype on our own through different alumni, through different individuals who were interested in seeing what we could do in a year. We sprinted to create a prototype in a year, which included partnering with a 3D printing company to create an Inconel 718 double unibody engine, which we designed as well as our superstructure, got some composite overwrap tanks, and designed our whole pressure system as well in that year. So we started there, we raised our money from there, and then we continued on in Hoboken just because that's where we started,
Yeah.
We probably had the same professors. I just got a PhD there.
Oh, very cool.
Very cool.
I bet.
Yeah, that was long.
Do you know?
What did you get PhD in?
I had studied mechanical and spacecraft navigation. That's how I
Nice.
check out.
Mechanical undergrad, mechanical grad.
Yeah, we can talk after.
Yeah, I would
Yeah.
love to talk to you.
So is that where all those pictures came from of you guys working on the rocket?
Yeah, most of the pictures of us working with rocket hardware are from our last testing campaign, which was after we graduated, but still through Stevens.
Yeah, the initial ones. We have some other photos up there
Yeah.
from a recent igniter test because we've been redesigning our igniter. So we recently did a test back in the spring, starting on some designs of that.
Yeah.
You guys
Have you guys done any feasibility studies on your rocket launchers?
Yes.
Yeah, feasibility study in...
Like in what regard?
Just to see what phase of development you're at and...
Oh yeah, totally. So our first generation vehicle has already been prototyped, and we're a good chunk of the way through testing. We've paused testing to focus on developing our payloads and really digging into the customer needs, because that's more essential than the launch vehicles when you're developing a service like this. We're also in parallel testing our engine. As Monica said, we ran igniter tests in July, and we're processing the results. Hope to run another test in a couple months. Bigger engine test in a couple months after that. First launch is scheduled for a year and a half-ish from now.
Fundraising pending.
And the larger suborbital vehicle and orbiter are in conceptual development. So mathematically they work, and in CAD they work, but parts haven't been made yet.
And in terms of market feasibility, we've done a couple of market deep dives ourselves and also contracted with a third party to help find things that we potentially couldn't. And with our suborbital reusable vehicle, we have found about a $6.6 billion total addressable market in 2020 dollars. and that expands to about 199 billion worldwide space economy for the recoverable factory. So,
What kind of engine thrusters are you guys using or planning to use?
So it's a 3D printed Inconel 718 unibody design with a coaxial injector that runs on RP1 locks.
Yeah, and that engine design, whilst engines aren't usually scalable, the core design concepts are. So we intend to use that particular design scaling across all of our launch vehicles, not necessarily in orbit, but
What does your software look like?
Good question. So, interestingly enough, our ground control systems are written in TypeScript,
Nice.
which is fairly new, right?
Oh, yeah.
I mean,
it's
yeah.
like
So
this.
most like aerospace companies will typically use it. They're just big companies. They're older. They're slower. They'll use like more legacy stuff. But
Yeah.
since we're new, we can use like the best of the best.
You don't see many doing that. It's pretty cool.
Yeah.
Sounds great.
And we're planning on using Rust for the actual in-flight
Really?
vehicle. Yeah.
Nice. Do you use that at all, or are you planning on it?
We
No.
haven't looked into it. That's a good point.
Alright.
Roast is my favorite.
Yeah, it was-
Yeah.
yeah, we've been focusing on the ground hardware right now. The launch hardware will come later, but being able to test stuff on the ground is essential to developing our vehicles quickly, and then also developing the payloads, which is really a big area of focus, being able to provide those tailor-made payloads to allow different science verticals to rapidly experiment and manufacture.
So forgive me if you already addressed this in the beginning, but how are you in the short term anyways differentiating yourselves between aircraft that do the parabolic flight versus what you're aiming to do in the short term?
a big thing there is like amount of time available in microgravity or in weightlessness. There was a slide Monica was doing that shows like the different times that you can achieve.
I don't think I included.
Parabolic flight.
Yeah, didn't include flying
That's a
parabolic.
good point.
Parabolic flight times are similar to suborbital flight times. The difference is really just cost.
In a parabolic flight, you get about 30 seconds of microgravity, and then it flies back up.
Yeah.
It does
So it's
that, like,
interrupted.
It's
like
cyclical.
10
Yeah.
times or
Microgravity,
something.
crushing gravity, microgravity, crushing gravity. So
I do believe it's also difficult to produce similar quality of microgravity. I think it's great for humans, but for experimentation, for instance, the best microgravity quality I think we get is on drop towers right now. I think it's
Terrestrially.
what?
Terrestrially. Right?
Yeah, and then it's difficult to get even good quality on suborbital as well. I think it's even more difficult on flights.
Yeah. The caveat, or I guess the redundant phrasing is microgravity means 10 to the negative sixth the force or the quality of gravity. So it's the technical designation of the type of environment that you find on your spacecraft. So in orbit around Earth, you can most likely get actual microgravity.
Thank you.
Yeah, thank you.
There's questions online from Mark from YouTube. He says, how expensive will sustained operations be? Or another way you could say, like, what's your runway that you have right now?
Our current runway is like 3 months. We're
startup vibe.
Yeah, we're in the middle of a fundraise, but we're on minimal R&D costs, just focusing on overhead because we're interacting with customers. Once we push through this current fundraise,
Yeah, it gets a little bit more. Once we push through this fundraise, I will be back doing more hardware R&D, and we'll be back up into approximately 20 to 25,000 a month on just the R&D alone. But general operations aside, it gets really difficult to plan out once we make that move out west, like we were talking about, or whatever else it is that we end up having to do. A lot of balls are up in the air, so those true like operations costs are variable.
And Mark also had another question, if you guys are hiring.
not yet, but I guess follow us on LinkedIn. Is that a thing? That's where we post job openings when they happen, and there'll also be a link on our website.
But if you're also interested in just having a chat with us, send us an email.
Yeah.
We're always happy to talk shop and to talk tech with people. So occasionally people will just come by and we'll talk about how our tech's going.
Sometimes people wander by the office and knock on the door.
Yeah.
And say, hey, I think what you're doing is cool. Let's talk.
Yeah.
Cool.
So hit us up if you're interested in talking.
Yeah, that's a good segue. Actually, we're planning of maybe organizing a tour of your facility, maybe at some point.
Yeah.
So that'd be pay attention to the meetup, and you guys can go check out the space.
That'd be awesome.
Curious to how you're approaching your current fundraising. If you're just looking for specific investors that are looking for a return, or if you're looking for companies that are potentially buying future rides on spacecraft, or through other funding vehicles such as like NIH or other maybe government entities.
Yeah, we just closed out our pre-seed round, so we're literally just preparing to jump into this next round. So the answer is going to be a little bit vague, but we are applying for government funding. SpaceWorks is a little bit of a mess right now, but we did NSF. We're planning on doing a conventional equity raise, and we are also exploring opportunities to partner with larger companies that may take advantage of our services in the future.
We're pretty flexible.
So have you looked at DIU, Defense Innovation Unit? Yeah.
If you look at SBIR.
Yes.
Yes.
Guys, just you're talking about micro ventures that you just finished.
Yes.
Okay.
We just closed. We closed a successful micro ventures campaign in like June.
Yeah, earlier this year. So.
Microventures is, for those who don't know, it's like a crowdfunding platform, kind of like Kickstarter, but you're investing in the company and you get a small amount of equity.
Yeah.
And you can invest with like $100 minimum.
Yeah.
Any other questions?
Can you just double check on that real quick?
I have a question.
Mhm.
So I know we kind of moved away from the technical questions, but I kind of want to bring it back.
Yeah,
Sorry.
Of course.
What kind of fuels are you planning to use?
So we're just using traditional RP1 logs right now in our current stage. It's pretty tried and true. There's a lot of a lot of information about it. Simple regenerative channels in the engine as well, and then a pressure fed system.
RP1 stands for rocket propellant 1.
Yeah.
And it's a form of kerosene.
Yep. It's actually really similar to diesel. It's just got a lot more quality requirements.
It's also used as jet fuel, right?
Yeah. No, we run all of our current tests with jet fuel because the performance characteristics are close enough that we don't have to pay for rocket fuel.
Yeah. Eventually, it's my dream that we will look at doing other propellants combinations, but we will need a bit of a beefier R&D budget and some revenue before we get to work on that. So.
Also a lot of the propellant assistance you get from using like a methalox system happens when you're using staged combustion systems. So we're not really going to be taking advantage of tons of that given a simple propulsion system. So at the time, it's just not worth it right now to look into it.
Yeah, I guess that's a detail that we glazed over, but a pressure fed cycle is literally the simplest way that you can build a liquid fueled rocket. It previously wasn't viable for larger rockets. There are a couple companies that have tried to develop vehicles in the past. They're not around, not because the technology wasn't viable, but because of business reasons. But because the technology is now viable, we can work with companies that manufacture composite tanks to achieve super high pressure liquefied gas in a super lightweight tank and use that to drive the pressure fed system. So no turbo pumps, no gas generators, no secondary turbines, nothing. We lose all of that weight, all of that complexity.
Yeah, and a lot of those components you mentioned are the ones that are super complicated and when things come back down have the most likelihood of failing. And so by eliminating those, we've also made our rocket more reusable, less costly.
Yeah, there was a quote from Elon recently that I saw. He said, one of the best things to do for engineering is to remove things.
Absolutely.
Yeah.
That's probably reporting too. Alright guys, we have to kind of be out of here by 7, so we'll have to start packing all this stuff up. Is there any last questions? And just double check online, I think we're good here.
Well, thank you guys for all your questions.
Yeah.
They were really great.
Thanks for coming to.
There are cards here in the middle.
Yeah.
Which have our contact info, and there are free stickers for your laptop or your bike or whatever.
I'm sure the link to the presentation will be floating around somewhere on our social or website if you guys want to see it later.
Yeah, and thank you to everyone who joined us over the feed. I'm not sure how many of you there were, but it was great to have you in attendance also.